So welcome to today's lab session. Today we are covering lab number 3. So it's the lab X3 if you look at the relevant file. And I'll share that link with you as well. Just give me a second. You can pick it up from the OneDrive folder. You've got the link in Blackboard, but I'll share that link again here. So that's the OneDrive folder, and just go to the labs folder, and then it's lab EX3. So you can find the handout for today's class there. So what are we going to do today? What we are going to do is to implement in VHDL a variable length shift register. And in fact, we are going to implement the variable length shift register that we've seen in one of our lectures, particularly in lecture number 8, slides 34 to 38. So we have most of the code already there in lecture 8. If you have a look, that's basically what we are going to cover today. So if you remember what we discussed about in terms of this variable length shift register, this was a direct application of using generic parameters and using generic mapping in order to create a universal length shift register. So this shift register essentially has a variable length which the user can set as they wish without having to modify the source code of the shift register at all. This was an example of a structural design where we had a component called DFF, which you see here. And that is a D-type flip-flop, a standard D-type flip-flop, which essentially, when the rising edge of the clock arrives, just says Q equal D. So it's the simplest type of D-type flip-flop, which we've already seen before. And this particular shift register connects a number of those D-type flip-flops depending on the size of n in there. And that would be our generic parameter, the length of the register. And all that is covered in lecture number 8. So again, from the implementation side, what we've done in lecture 8 already would be captured in 2 source files. You will have one source file called DFF, which implements the code for a D-type flip-flop. Then as part of shift, you will define DFF as a component and essentially do what we've done in lecture 8. You can just go to slides 34 to 38 in lecture 8 and just copy paste the stuff from there as mentioned later on in this handout. So in terms of the implementation, first of all, we need to create the code for the variable length shift register. To do that, we are going to create a new project in VHDL. So you start the project navigator, create a new project, and you can call it lab 3. Then when it's asking you, just make sure, of course, that you set the language as VHDL. You can leave the devices as they are. When it's asking you for a new source, select VHDL module and then call it shift. Once you have typed shift in there, you can just click next, next, and finish without actually setting anything in the graphical wizard of the entity, because basically what we are going to do is just copy paste the code from slides 34 to 38 in lecture 8 in there automatically. So there's no point in us setting the ports, since that will be done when we do the copy pasting of the code from lecture 8. So once we copy the code from lecture 8 and paste it in the Shift VHD file that we've just created, the next thing to do is to change everywhere where it says bit, change that to std_logic, and everywhere where it says bit_vector, change that to std_logic_vector. So basically we use standard units, which is always the best thing to do. At that point, we've basically got the source code for Shift, and that will reside into this file called shift.vhd. Next thing would be to create the code for the D-type flip-flop. So to do that, we are going to create a new source. Again, you will choose a VHDL module, and this time you are calling it DFF. This would be then, in terms of the code, a standard D-type flip-flop, and this would be then the subcomponent that is defined inside of Shift. The ports for it, when it's asking, would be D, clock, and Q, and they're all single lines. So this time, no bosses whatsoever. As usual, once you've done Shift, check for errors. Then once you've added the new source file for DFF, again, check for errors before moving any forward. Once you have the two source files and you save them, if everything is fine and you haven't got any errors, you will then see that DFF will sit as a subcomponent of Shift. So at this point, we have the complete code that we have covered in our lecture number 8. And that will implement a variable length shift register. Now, that is defined as a variable length. In order to use it, we would need to actually create a new source file where we define its size. So step number 2 would be to use the variable length shift register. To do that, we need to specify what the size is. So we are going to create a new source file. This would be again a VHDL module, and you can call it top. Top will have exactly the same ports as Shift. The only difference is that this time the entity will no longer have any sort of generic parameter, so it will have a standard entity as created by the VHDL entity generator. Then, as part of top, we need to define Shift as a component of it. You can do that just as we normally do, just copy basically the whole entity of Shift, paste it before the begin of top, and then change the word entity to component, and then say end component. And then after the begin, we need one line there which does a generic map and a port map in order to specify what the size of the register is and to port map it into top. And you can see an example of how to do that on slide 38 of lecture 8. Again, check for errors, and if everything is fine, then you should see now that Shift is a component of top and DFF is a component of Shift. And if there are no errors and anything, then the last thing to do would be to simulate this design. You can add a graphical test bench. In other words, go for new source and select test bench waveform, set the input signal, and then create a behavioral simulation for this design. So all in all, at the end of the day, your design will look like this in terms of its hierarchical view. You will basically have DFF, which is a subcomponent of Shift, and then Shift would be like a subcomponent of top. And again, in terms of the relevant ports, you will have, when you do the port mapping, port A of Shift linking with port A of top, port clock of Shift linking with port clock of top, and then port B of Shift linking with port B of top. So very simple no linking signals required. You just basically connect shift into top. But the only difference is that you've also got a generic map there as noted in the previous slide to allow you to do the implementation. So as far as the relevant ports are concerned, for DFF you'll have D, Q, and clock. For shift you'll have A, clock, and B, and for top you'll have A, clock, and B as well. So that's pretty much in a nutshell today's lab. What we want to do is to see how to use one of these generic size or generic length shift registers that we've looked at as an example in our lecture number 8. So just follow the instructions from this handout. If we go to Xilinx, you would have created a new project called Lab 3, and your hierarchical view should look something like this. So we started with shift, which you would have copy-pasted from lecture number 8, and then changed all bit to standard logic and all bit vector to standard logic vector. So the code will look something like this. In the lecture, we don't really have the code for the DFF component yet, so that would have been the next one to implement. So the easiest way basically to do a D-type flip-flop would be to say if clock event and clock equal 1, then Q equal D. So you either write that by hand or as usual, you can go to language templates. So edit, language templates, VHDL, synthesis constructs, coding examples, and then we're after flip-flops, D flip-flop, positive edge, and it's the simple register. And then you just customize that one basically. So once you write the D-type flip-flop, it will look something like this. And then as soon as you save it, you'll see shift and then 3 of those labels, which are right, left, and FFS, which are the D-type flip-flops sitting underneath it. So that is because we have this port mapping operation, then which is the right label. Then for the left label, we have that port mapping. And then for the FFS, we have the ones inside of the generate statement there. So nothing of that is really new. It's pretty much the code from our lecture number 8. What's unique about it is this generic parameter here, which it's part of the entity of our shift register. So this basically defines a generic parameter called len, which is an integer and by default is not initialized with anything. So we don't really know what the length of this design is. It's just a generic length len. And we always basically refer to that len in our code. So to be able to use this design, which at the moment looks like this, we have this shift register, and then we have the inner D-type flip-flops, all with a size of len. To be able to do that, we need to embed this shift as a component. So if we go to the overall code structure, then it will pretty much look like this. So we have now the shift with the DFF components sorted out. And all we need to do is to put another box on top of it for top. And then as part of that, we are going to do a generic map and a port map. So if we go to the code and we look at the code for top, it's very simple really. So it will have the same ports as our shift register. We then define our shift register as a subcomponent of top before the begin. No need for any linking signals because we just link the ports in a straightforward fashion. So you notice that len is there as a generic parameter when we define the shift component. So the usual way we do is to just copy the entity of shift from the shift file, go to top, paste it here, and then replace entity with component and say end component. So now we have defined shift as part of top. And then basically what we need to do here, and this is the unique thing, is for our component shift, we now specify what its length is. So len is now going to be 10 in my example. And then we have a port map which just links A with A, clock with clock, and respectively B with B. So it's as simple as that. And you can see how now top sits on top of everything, shift being a subcomponent of it, and then the flip-flops being a subcomponent of shift. So far so good. We have all that. We check for errors just to make sure everything is fine. There you go, all good. So the next step would be to add a test bench in order to simulate. So just create new source, and this time we want a test bench waveform. Let's just call it TB. In my case, it's complaining that it's already there. That's fine. I'll just overwrite it. So it is linked with top as expected. And then you go for next, and finish. And we can use some of those timings that we have in our labs folder. So make it 10, 10, 5, 5, 10, and respectively 10. And we will end up with a test bench which looks like this. So the only input which we have really that we can modify is A. So if I then set it up, so something like that, then we should be able to see it. We can see that top sits underneath it. So let's just go ahead and simulate. There you go. This time is working. So there you go. This is the result of the simulation. Now, remember in my example, we have selected a 10-stage shift register. So the length is 10. So it's got basically 10 D-type flip-flops in it because len has been set to 10. So this 10 would be mapped to len as part of the generic map operation. So if we go to the simulation, you'll notice that the output is undefined for 10 clock cycles. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And on the 10th clock cycle, what we have are the input there, which is that 0 for A when the clock arrives. That one now is put at the output. And you see that between that point and this point, that chunk of time now is here. Then we have that chunk, which is shown in here. So basically the output is delayed by 10 clock cycles. Because essentially, if we look at the schematic, we have 10 of these D-type flip-flops, and each flip-flop essentially adds 1 clock delay for the information at its input to go to its output. So it would take, since I've got 10 of these flip-flops, it would take 10 clock cycles to go, or for that signal A to propagate from one flip-flop to the next, 1 time per clock, and for it to finally arrive at the output B. So you see how essentially the output from that point onwards would be the input shifted essentially by 10 clock cycles. So we have this shift operation which is done clock after clock. So it will take 10 clock cycles between that point to the output. And there's 10 clock cycles between that point and this point, 10 clock cycles between that and this, 10 between this one and that one. So the output is essentially delayed by 10 clock cycles. So you could look at this either as a shift register or as a delay line, which delays by 10 clock cycles, or however many D-type flip-flops you've got. So if I want to change its behavior, I don't need to make any changes to shift because that is universal in size. If I want to use this with 5 flip-flops instead of 10, I just change this in generic mapping at the top level. No need to change anything in top. If I then go back and simulate the design again, now you should see that the output is delayed by 5 clock cycles as soon as the simulation pops up. So simulate behavioral model once more. Here we go. So you can see now that because I've made that change and I've got 5 flip-flops instead of 10, looking at the simulation waveform, between that point and this point, or between that point and that point, there are 5 clock cycles. Now between this point and that point, it's a delay of 5 clocks. Between that point and this point, a delay of 5 clocks, so on and so forth. So the output is basically always synchronized with the clock and delayed by 5 clock cycles. So again, in terms of the behavior, this time we have a 5-stage shift register, which delays the output signal by 5 clock cycles in this instance. So there you go. That's pretty much in a nutshell what today's lab is all about. And this shows really the importance of having generic length components, because we don't have to change anything in shift if we want this to be a much larger or much smaller shift register. The only change we need to make is when we use it as part of some other program, is to change the size of that len as part of the generic map, and the rest basically stays the same. We don't need to make any of the changes at all to the internal shift register itself. So no changes in the shift.vhd code. The only change would be in top when we use this design. So it's embedding it without any change in top, and as part of top we can specify essentially what its size is going to be without having to touch the code for our shift register at all. The other thing I would mention, if you haven't done so already, if you want to change the color scheme so yours is showing using the lighter color scheme, again as usual you go to Edit, Preferences, so last option in the edit menu. And then in there you have the IIC simulator. If you expand that and click on simulation waveform colors, if yours is on a black background, it will say default in there. Just make it classic, apply and OK. And then next time when you run the simulation, it will basically be shown using the new color scheme. So there you go.